So the Case and Design Basis tab allows us to select what type of design we want to carry out. Level 2 would be work and stress design, which is what we use the majority of the time in the industry. And level 3 is limit state design. And finally, level 4 is reliability-based design, where we can look at the historical strength of pipe being created by a reputable mill, and then use that to calculate the probability of failure for load cases which fail standard work and stress design. And then we can utilize this in survival load cases to potentially justify a design that has a safety factor below our design factors, or even a safety factor below 1. So in the design basis here, when you switch between level 2 design, your work and stress design, which is what most people will be familiar with from, say, a program like WellCat or Stress Check, we have these bits of data that we can enter. And then when we have reliability-based design, there's a few more other pieces of data that you would need to reach out to a pipe manufacturer to gather this, like the KISSC. You need to find that in the burst strength factor. Was the pipe normalized? As in, once it was created, was it just let to cool naturally, or was it quenched? Was it cooled down quickly? And this affects the burst strength factor. So we're going to go for reliability-based design, because when I continue forward, I'll be explaining that module as well. And when I explain that module, we need that active. So we had just looked at this string here, and originally this would have been 12.5%. So this 12.5 comes from the beginning of the API burst equation, which, if you remember, is 0.875 times. And it's at 0.875, or the 12.5%, which allows us to put in sort of a buffer margin for manufacturing tolerances. So we can see on this data sheet, and this is actually the 10 3/4. Let's go to the 10.175. On this data sheet here, it states based on 90% remaining body wall, minimal internal yield, or burst rating. So we come across here, and wall tolerance for the 10 3/4, for the 10.175, it changes to 10%. Remaining body wall, if you wanted to model some sort of wear, let's say we wanted to model 20% wear in a pipe, which would be uniform wear, not groove wear. So it's a quick check. I could change this to 80%, and that'll adjust my ratings of tubulars by that 20%, as if 20% of the wall had been taken away. This is a fresh design, so we're not looking at that. And I don't expect too much wear in a tieback. Although, if some sort of corrosion study was to be carried out, then we could reduce these remaining body wall numbers and see what sort of effect corrosion would have on our design. Imperfection depth. This is an indication of the depth of the imperfection that the mill can detect when they're carrying out inspections later on. Finally, the last bit on the design basis, we've got our minimal acceptable safety factors here. We did one for casing and one for tubing. So whatever's in the case and design manual, yeah, they're in here. Most people use 1.25. Some people use 1.31 for triaxial. It depends on corporate policy. So I'll just stay with standards here. So we'll just use these minimal acceptable safety factors here. So as we move forward into the design, before I get there, I want to make sure that the strengths that the program is using, or the strengths that I want the program to use. So we've created connections, we've created tubulars, and then we've got maybe a remaining body wall difference. We want to predict where, or there's wall tolerance. We're now at this 10%. So what I need to do, or what I can quickly show you, is if we take this 10.175 and put it back to the default 12.5, when I come across the tubular performance, which states what numbers the program is going to use going forward, I can look at the burst pressure rating here, and it's 17.199, which doesn't tie in with our minimal internal yield here of 17.690. So I would have to come back across, change this to my 10%, so 10% remaining body wall here, or wall tolerance, interchangeable terms. I come back across to my tubular here, and I'm 17.690, which ties in exactly with what this is here. And then we can see actually the collapse strength here is a tiny, tiny bit out. So the SOVAM here have rounded down to the nearest 10 psi. which it didn't do for KIPS, but they've done for PSI here. So if we wanted to be consistent, we could change this. So all we would need to do is right click here, proprietary tubular information, as per VAM data sheet. I'm going to change my proprietary tubular information to 17340. Click OK. Next thing you come across here. For connection performance, I can check these numbers here against the numbers that are displayed here. And I've just done that before I started recording the video, so another correct. 24071685, just another quick check. Yeah, so we're fine. So everything in these yellow boxes here are the numbers that the program is going to carry forward into the stress calculator and stress results. So if these numbers don't match what you see on a data sheet or what you perceive as the strength at the time the load's taking place, then changes need to be made here. Because we've got level 4 reliability-based design selected, we also have a few other ratings here. We've got the ISO 10400 ductile rupture pressure. We've got the ISO 10400 cleaver generalized Tamano collapse pressure, and then we've got the ISO 10400 brittle fracture pressure. These ratings here. And you see this is now changed to proprietary because we just changed this number by 4 psi. It's no longer an API tubular type, it's a proprietary piece of pipe or connection. And this highlights it for us. You'll also notice when we come back to our casing program here, that the same piece of data is displayed. We've got proprietary information there. Okay, so we've now finished the casing design tab, and quickly before we move on, I'll show you the feature of our sidekick. So this is our casing program as put into the spreadsheet format. However, if we wanted to visualize this, we need our schematic. And what we call the schematic in StrinGnosis is the sidekick. It's this button here. And the sidekick can be accessed from any screen, any box inside the program. So if you've got a box open, there'll be a button up here so you can go straight into the sidekick. Normally, I'll just store the sidekick on my second monitor and use it as a reference. The main part of the sidekick is the wellbore diagram, wellbore drawn even, and this displays the well here. You can right click, a lot of options of potential changes you want to make. We've also included a TVD MD calculator. So if I wanted to know, I'd say 14,000 feet, what my TVD was, or more importantly, what my pore pressures and fracture gradient are, and temperature are at that point. If I'm creating some sort of custom load later on, then I can use this as a reference. We also have a small fluid calculator where you can enter in the pressure and temperature of water, black oil, and methane. It'll give you a density, it'll give you compressibility, and maybe your Joule-Thomson coefficient. If you need data like that, it gives you all the data you've got. Finally, we've got a completion diagram, which is almost just a simplified version of the wellbore diagram. But if we had included any sort of completion equipment, they would be displayed here with depths along the tubing here. We have a reference here to the 6-inch production tube in the hydraulic packer, which we've selected. So I'm going to finish up now on casing design. We're going to move across to the stress calculator and show you how to build loads.